Okay, in this one, I want to do a few examples of that first case of solving second order homogeneous linear differential equations with constant coefficients, where in the characteristic equation, we have two distinct and real roots. Quick review, because it's always worthwhile just to repeat ourselves a little bit. The idea behind solving these kinds of equations, and remember the kind of equation that I'm talking about is this one, y double prime plus py prime plus qy equals 0, where p and q are constants here. That's what I mean by a second order homogeneous linear differential equation with constant coefficients, okay? Is that we guess that y equals rx is the solution, okay? Under this scenario, you can, of course, explicitly compute y prime, y double prime, and plug all of that into your second order homogeneous linear differential equation with constant coefficients. And what you come up with in the end is this polynomial equation in R. Have a name for this. We call that the characteristic equation, or characteristic polynomial, as it's sometimes called. And there are any number of ways of solving this that you learned at various points in your life. I remember it was interminable. And we spent so much time talking about different ways of solving. One way is factoring. Sometimes factoring doesn't work, in which case you might do completing the square, which is really equivalent to the quadratic formula. Okay, so that's what we used here. We used the quadratic formula. When you use the quadratic formula, you quickly learn that there are three cases that are determined by the sign of something called the discriminant. The discriminant is a quantity associated to the quadratic equation, which discriminates between the three cases that I'm going to describe here. If the discriminant is positive, then you have two real roots, R1 and R2, which are distinct and real roots. Okay? In which case, it's very easy to write down the general solution. You just backtrack, you realize R can be one of those two real roots, though that represents two possible linearly independent solutions. Then you mash them together in a linear combination or a superposition to obtain the general solution. In the case where p squared minus 4q is exactly 0, the discriminant is exactly 0, you only have one root, which we call R, which we're calling R. In which case, e to the rx and x e to the rx turn out to be solutions in this case. I can give a little bit of color on that when we come to that case, which maybe I'll do in a third video. Finally, we have the case where p squared minus 4q is negative. And that's where we have complex roots. And in some sense, this is going to be the most important case for us, okay? And so I'm going to devote a significant time to fleshing out that story, okay? But that's for a separate set of videos. What we want to do now is do some examples, just to make sure that we understand. So second order homogeneous linear differential equations with constant coefficients examples. So here is an example. Let's do y double prime plus, or how about minus 6y. Wait, how does I vaguely know how this works. Plus 6y prime plus 5y equals 0. How about that? I think it should be plus 5y. I want to make it easy to factor, okay? So I want to make the characteristic polynomial easy to factor, okay? So this is my second order homogeneous linear differential equation with constant coefficients, okay, great. We can immediately write down the characteristic equation. And I'll just write char equation. This is going to be r squared minus 6r plus 5 equals 0, okay? And again, I insist that you should know ways of solving this equation in all situations, okay? One way that I believe, oh god, yeah, it works. Okay, one way that I think works here is that this thing factors. I think it factors into r minus 5 and r minus 1. And plus 5. Yeah, it works. Okay, miracle. Great. And so you don't need to resort to the quadratic equation. You can just go immediately to factoring if that's your preferred way. All right. And of course, what this implies by the zero product property is that R is equal to 5 or 1. Now, what that implies is that we can immediately leap to the general solution. The general solution to the differential equation is y equals C1 times e to the 5x plus C2 times e to the 1x. So what's playing the role of R here? Remember, our atoms, our linearly independent solutions are going to look like e to the rx. And if R is different and real, these are going to be linearly independent solutions, and we just mash them together in this linear combination, this superposition expression like this. And nobody bothers to write 1x. That's weird. So we just write x. Okay, and that's our general solution. And that's the solution to this differential equation. And I mean, it means you can, in particular, check this. You can take y prime, y double prime of this general solution, plunge all of that data back into the original differential equation, and it'll all check out. Okay? Okay, cool. Now, what if we were given some initial conditions? So what if I said we have this problem, same problem, y double prime minus 6y prime plus 5y equals 0. It looks the same, but then I'm going to toss in some initial conditions. Now, initial conditions for second order equations look something like this. Y of 0 is equal to, I don't know, 3? I'm just making things up. And how about y prime of 0 being equal to, I don't know, negative 7? I'm really just making things up. I don't know what I'm doing. Oh, this might be really gross, but we'll see. It's okay. I'm not scared. Am I not scared? I think I'm not scared. I don't know. We'll see. Okay, what happens when you toss in initial conditions like this? Well, we know the general solution already. It's y equals C1. I don't know why I'm copying, but I feel compelled to do it all under this problem here. So this is the general solution that we found in the first chunk. And the point about these initial conditions is that they are like specifications which are going to allow us to pin down the values of C1 and C2 here, right? We're going to be able to use these initial conditions to figure out the specific values of C1 and C2, which make this general solution here conform and to these specifications. Okay, what does that look like? Well, let's take the first one first. So y of 0 is 3. This implies, of course, 3 is what I get by plugging 0 in for y. I just wrote it in the other. I don't know why I do this. I'm sorry. And y of 0 is simply C1 plus C2. Do you see that? Because when you plug in 0 in for x, in either of these exponentials, you get 1. E to the 0 is 1. So that gives me an equation, C1 plus C2 is equal to 3. Now, what about the other equation? Y prime of 0 is equal to negative 7, the other initial condition. Well, that tells me 7 is equal to y prime of 0. Y prime, in general, is 5c1 e to the 5x plus c2 e to the x, right? I just took a derivative, and I didn't forget the chain rule because I'm not a child. So I plug in 0 into that expression, and I get 5c1 plus c2. Okay? And what I want you to see is that I've got a system of equations now. This is a system of linear equations. In C1 and C2. And I need to find the values of C1 and C2 which satisfy both of these simultaneously. Okay? And there's lots of ways of doing this. One way that you could do this is subtract one equation from the other to cancel out the C2. But let me just show you the sort of general way to approach any problem of this sort. It's to solve for one of the variables, one of the constants, in terms of the other. So let's solve for C1 in terms of C2, for example. If I do that, if I take this first equation here, I learned that 3 minus C1 is equal to C2. Yeah? And then I can take this expression for C2 and plug it into the second equation. I can take this, plug it into here. And if I do that, I get that 7 is equal to 5C1 plus 3 minus C2. C1, I'm sorry. I vaguely know what I'm saying out loud. And this is like, you know, an 8th grade algebra problem. We just, right, 7 is equal to 4C1 plus 3. 4 is equal to 4C1. And I guess C1 then 4 is 1. I have no idea how the number came out that cleanly. If you think that I have the brain power to think that far ahead in life, you are, well, thanks. It's really kind of you, but you are sadly mistaken. Okay, so that's C1. And now how can we figure out C2 from this? Well, we know a relationship between C1 and C2 right here. We can take this value of C1, that it's 1, and put it and use this equation to conclude that C2 is in fact equal to 3 minus 1, which is 2. So this gets me C1 and C2, meaning that my solution to the IVP, that is the differential equation together with the initial conditions, is given by y equals C1, which is 1, so e to the 5x, nobody bothers writing 1 out front, that's weird, plus 2 times e to the x. Do you see how I did this, please? Just to be clear, I took this information for about C1 and C2 and put it into the general solution, and I ended up with this particular expression, which solves not only the differential equation, but also solves the initial conditions. Okay, makes sense? Let's do a problem, another one. How about we have something like, okay, how about y double prime minus y prime plus y equals 0. Okay, so this is a second order, why did I do this? Second order homogeneous linear differential equation with constant coefficients, okay? We can immediately write down what's called the characteristic equation, so let's do that. The characteristic equation in this case is r squared minus r plus 1. I don't know, I'm a little scared. Is this going to be complex roots? I don't know, we'll see. Equals 0. In which case, we should probably use the quadratic formula for solving this one. We get that r is equal to negative 1. So what's playing the role of b here is negative 1. So negative 1, which is 1, plus or minus the square root of 1 squared, which is 1, minus 4 times 1 times 1. So that's minus 4. So the problem here in this example is that I'm going to get complex roots. Okay, so you know what I'm going to do? We are going to pretend this never happened, and I can't bear to redo the video. So we're going to change that plus that was there. We're going to change it to a minus and pretend that it never happened. Okay? Because now, what is the characteristic equation? It's r squared minus r minus 1. So in the quadratic formula, we have 1 plus or minus the square root of negative 1 squared, which is 1, minus 4 times 1 times negative 1. Negative 1 now. Yeah? You following me? And so we get 1 plus 4. Ah, nice. The whole thing divided by 2. So this ends up being 1/2 plus or minus the square root of 5 over 2. And what I want to say is that this is what's playing the role of my R1 and R2 now. Yeah? We can take R1 to be the positive one and R2 to be the negative one. In which case the general solution, oh, let me do this in purple. The general solution to the differential equation is going to be y equals C1 times the exponential of R1 times x. Now, that's a messy R1 there, so I'm going to write it like this. Exp of 1/2 plus square root of 5 over 2 times x. You see the value of the exp notation, the inline notation. Plus C2 times exp of 1/2 minus the square root of 5 over 2, and I need another parentheses here, times x, and that's it. What could be easier, right? This is so easy. Great. Yeah. One more example, and then we'll call it a video. Let's say that we have something like, I don't know. Sure. How about this? Do I mean it? Yes, I do. M times y double prime minus k y. Yeah, ky equals 0. Okay. Here, we're going to take m and k to be positive constants. Okay. Okay. Then what is the characteristic equation? Oh, sorry. No. Well, whatever. The characteristic equation in this case, and I guess when I defined everything, I sort of assumed that the coefficient in front of y double prime was 1. So maybe to bring everything into conformity with that, I can do the same thing here. How? By dividing everything in sight by m. If I divide everything in sight by m, I get that this equation here is equivalent to y double prime minus k over m times y equals 0. You see, I just divided both sides by m. In which case, the characteristic equation is r squared minus k over m equals 0. Yeah? Please make sure you understand how that happened. In which case, the solutions are, this is equivalent to r being equal to, so add k over m to both sides, take the square root of both sides, you get that the absolute value of r is equal to the square root of k over m. So the r is equal to plus or minus the square root of k over m. If any of that was mysterious, make sure that you go back and study and review that. So that the general solution and by the way, the square root of k over m is a real number precisely because m and k are positive constants here. Let me just think for a second. Why is this hurting my feelings a little bit? Should it be? Sometimes I get these weird feelings like I'm doing something terribly wrong. But I don't see it. I think we're all good. Okay, general solution. I'm paranoid, okay? I have paranoia, mathematical paranoia. And that's healthy as long as you know how to manage it, okay? Don't let it take over your life. I sometimes get emails from people. Anyway, let's see. R is equal to plus or minus the square root of k over m. So the general solution is going to be y equals the exponential of square root of k over m. Oh, I'm sorry, and I messed up. Let me fix myself. Times x. Let me move this over a little bit, like this. Move it just like there, and because I need a C1 in front, of course. I need a C1 in front. Yeah. Plus C2 times the exponential of negative square root of k over m, the other root, times x. And that's the general solution. Okay. It all comes down to solving a quadratic, okay, in each of these situations. And we saw here, we solved the quadratic using good old factoring. Yeah, it's great. And then we used the quadratic formula in this one to solve that guy. And that worked great. And by the way, the quadratic formula will always work because the quadratic formula is a nuclear weapon that will destroy anything that you come across. That's a quadratic quadratic equation. And finally, we just use good old taking the square root of both sides type thing on this last one. All right, but the point is about how you construct these general solutions here. Okay, that's enough for this one. See you in the next one where we'll talk about repeated roots.